Designing microservice architectures. One of the first steps in designing a microservice architecture is defining service boundaries. This involves understanding business capabilities and domain logic to properly isolate services. Properly defined boundaries ensure services are loosely coupled and can evolve independently. In this context, we don't have specific code since it's a high-level design concept. Defining service boundaries usually starts with domain-driven design, DDD, techniques such as bounded contexts, which help to clarify the limits of each microservice's responsibility. Domain-driven design, DDD concepts. In DDD, an aggregate is a cluster of domain objects that can be treated as a single unit for data changes. Each aggregate has a root and a boundary defined around it. The root is the only member of the aggregate that outside objects are allowed to hold references to. Inter-service communication patterns. In a microservices architecture, services need to communicate with one another. One common approach is to use RESTful APIs. Spring Boot makes creating REST endpoints and clients straightforward with the @REST controller annotation for services and REST template or web client for clients. The code provides an example of a service, Service 1, defining a REST API endpoint to fetch a product by ID using the get mapping annotation. It declares a product service class with a getProduct method that is mapped to a GET request at /products ID. Service 2 consumes this endpoint using REST template to call the product service and requests the product, where product service is expected to be registered in a service discovery. Configuring microservices with Spring Boot. In Spring Boot, configuration is typically handled through a properties file named application.properties or application.yml. These files allow developers to externalize configuration so that the same application code can be used in different environments. In the provided code snippet, server.port is set to 8080, which is the port that the microservice will listen on. The spring.application.name is set to myMicroservice, giving the application a name that can be used when communicating with other services, such as when registering with a discovery server. These properties can be overridden at runtime using various mechanisms supported by Spring Boot. Service registration and discovery. In a microservice architecture, service registration and discovery are key components that enable services to find and communicate with each other. Spring Cloud provides a solution to this problem with Netflix Eureka. The provided code is a simplified version of a Spring Boot application enabled with Netflix Eureka for service registration. The @enable Eureka client annotation is used to make the application act as a Eureka client, which registers the service with a Eureka server. This setup enables the application to locate other services through Eureka's discovery mechanism. The actual implementation requires Eureka server setup and additional configuration properties for client services. Externalizing configuration. Spring Boot allows externalizing configuration so that you can work with the same application code in different environments. You can use properties files, YAML files, environment variables, and command line arguments to externalize configuration. Application.properties is one of the default files Spring Boot uses for configuration. This application.properties file specifies the server port to 8081 and configures database connection properties, including URL, username, and password. Fault tolerance patterns. In a distributed system like microservices, several things can go wrong, such as network issues, service unavailability, or high latency. Fault tolerance patterns help systems to handle and recover from these issues gracefully. Here we will discuss common patterns like retry, circuit breaker, fallback, and timeout. We won't include code at this point, as this is a high-level introduction to the fault tolerance patterns available for microservices architectures. Implementations of these patterns are commonly provided by libraries like Netflix Hystrix or Resilience4j in the Spring ecosystem. Distributed tracing and monitoring. In a microservice architecture, services often communicate over a network to fulfill a request. When something goes wrong, it's important to be able to trace the flow of requests across service boundaries to understand the underlying issues. This is where distributed tracing comes in. Spring Cloud's Sleuth is one such tool that integrates with Spring Boot apps to provide distributed tracing. Additionally, Spring Cloud supports integration with Zipkin, a distributed tracing system, to visualize traces. The first part of the code snippet includes Maven dependencies for Spring Cloud Sleuth and Sleuth Zipkin, which need to be added to your build file. After adding these dependencies, Sleuth will automatically start tracing all incoming and outgoing requests. However, to view these traces, you need Zipkin or another compatible distributed tracing system. The second part of the code configures sampling, in this case, to always sample every request, so that they will be available for viewing in Zipkin. You can customize the sampling rate based on your application's needs. Gateway and Edge services. In a microservices architecture, a gateway is an entry point for clients to access various microservices. It acts as a reverse proxy, routing requests to the appropriate service. Edge services are often responsible for concerns such as security, load balancing, and monitoring. Spring Cloud Gateway is a project that allows you to build an API gateway on top of Spring WebFlux. This code demonstrates how to set up a simple route within Spring Cloud Gateway. Scaling microservices and load balancing. In a microservices architecture, scaling is essential for managing increased load and ensuring high availability. There are two types of scaling, horizontal and vertical. Horizontal scaling, or scaling out, involves adding more instances of a microservice. Vertical scaling, or scaling up, means increasing the resources, CPU memory, of an existing instance. Spring Boot microservices can be easily scaled horizontally by running multiple instances. There is no specific code snippet associated with the concept of scaling, as it is more of an architectural and operational practice. Scaling would involve configuring deployment files or using orchestration tools like Kubernetes to manage multiple service instances. Spring Caching Abstraction, EhCache, Redis. The Spring Caching Abstraction provides a consistent approach to caching across different cache providers like EhCache, Redis, among others. It abstracts the actual cache implementation from the developer, allowing them to add caching to their applications without being tied to a specific implementation of caching. This means you can easily switch between different caching solutions with minimal impact on your code. In this code snippet, the @cacheable annotation indicates that the result of the findBook method should be cached. The cache itself is named books. When a method annotated with @cacheable is invoked, Spring looks in the cache before actually executing the method. If the cache contains the desired result, it is returned immediately, bypassing the method execution. Otherwise, the method is executed and the result is added to the cache. EhCache or Redis would be the underlying cache implementation, but the business code does not need to be aware of the specific details of the cache being used. Spring Batch Processing. Spring Batch is a lightweight, comprehensive framework designed to facilitate the development of robust batch applications vital for the daily operations of enterprise systems. It provides advanced functionalities for batch jobs, including logging, tracing, transaction management, job processing statistics, job restart, skip, and resource management. This code snippet shows a basic configuration class for a Spring Batch job. It leverages enable batch processing to enable batch processing support and configure standard Spring components. The example job bean defines a job with a unique name, run ID incrementer, listener, and step sequence. The @bean annotation declares Spring-managed beans, such as jobs and steps, that work together to process large volumes of records. The job builder factory and step builder factory are used to construct the job and step definitions, respectively. Additional components like item reader, item processor, and item writer are not shown but would be declared similarly. Spring Session Management. Spring Session provides an API and implementations for managing a user's session information. It aims to support clustered sessions, multiple sessions in a single browser, and RESTful APIs where session IDs are not typically sent as cookies. Here is a basic example of configuring Spring Session in a Spring Boot application. In the given code, we have used the @enable Redis HTTP session annotation on a configuration class to enable support for a distributed session management using Redis. This requires Redis to be set up as the session store, which allows Spring Session to store session information outside the application container in a Redis data store. This is useful for scalable applications and preserves session data in case of application restarts. We do not include session configuration settings in the example. However, in a real-world situation, you would specify Redis connection details and other session-related settings within the configuration class. Internationalization in Spring. Internationalization, often abbreviated as I18N, refers to the process of designing a software application so that it can be adapted to various languages and regions without engineering changes. In the context of Spring, internationalization is achieved by defining locale-specific message sources that the application can use to serve localized messages to the user. In the provided code, we define a message service class that uses a message source bean to retrieve localized messages. The message source.getMessage method takes an ID representing the message, an array of objects that can be used to fill in placeholders within the message, null in this case, and the current locale determined by locale-context-holder.getLocale. An instance of resource bundle message source can be configured as the message source in the Spring context to read localizations from properties files. Handling file uploads with Spring. Handling file uploads in Spring is a common task where users need to upload files to the server. Spring provides support for multi-part file uploads by integrating Apache Commons file upload and Servlet 3.0 multi-part request passing. To handle file uploads, you need to configure multi-part support, create a controller to handle post requests with multi-part form data, and process the uploaded file. In this code snippet, we define a REST controller file upload controller with a method handleFileUpload to handle file uploads. The @post mapping annotation maps upload path to the handleFileUpload method for post requests. The @requestParam annotation indicates that a parameter file will be bound to a multi-part file object which represents the uploaded file. Inside the method, we might perform operations such as saving the file. If the file is successfully handled, the method returns a success message. In case of failure, it catches the exception and returns an error message with details. Advanced Spring Boot features. Spring Boot Actuator is an essential feature of Spring Boot that provides production-ready features to monitor and manage your application. Actuator exposes various endpoints to provide operational information about the running application, health, metrics, info, dump, env, and more. You can customize these endpoints according to your needs. Spring Application Events. In Spring, application events allow us to hook into the Spring lifecycle and context behavior with our own custom logic. Spring Framework provides several built-in events, but you can also create your own. Listeners can then be defined to react to those events. In the provided code, we define a listener, custom Spring Event Listener, that implements Application Listener with the generic parameter context-refreshed-event. The onApplicationEvent method is the callback that gets invoked when the context-refreshed-event is published, which typically occurs when the application context is initialized or refreshed. In this case, when the event is published, the console will print context-refreshed-event triggered, indicating that the listener has responded to the event. JMX integration with Spring. Java Management Extensions, JMX, is a Java technology that supplies tools for managing and monitoring applications, system objects, devices, and service-oriented networks. Those resources are represented by objects called mbeans, management beans. Spring provides support for exporting any Spring-managed bean to a JMX server, as well as for accessing JMX attributes and operations directly. This mechanism is beneficial for controlling and configuring applications in runtime. The code snippet defines a simple Spring-managed bean with JMX annotations. The managed resource annotation signifies that this bean should be exposed for management via JMX. The object name attribute must be unique and typically follows the format of domain name equals myMbean name. This mbean has a single attribute value, with associated getter and setter methods that are annotated with @managedAttribute. By annotating the getter and setter with this, you expose the attribute through JMX, which then allows it to be read and modified by a JMX client. You would also create a configuration to export this bean, but this code focuses only on defining the mbean itself. Building WebSocket applications with STOMP. WebSocket is a protocol that provides full duplex communication channels over a single TCP connection. Spring Framework simplifies the building of interactive web applications with WebSockets using STOMP, which stands for Simple Text-Oriented Messaging Protocol. STOMP provides a messaging template and annotations to create WebSocket message handlers. In this code snippet, we define a WebSocket controller with the @controller annotation. The @message mapping annotation ensures that messages sent to hello will be handled by the greeting method. The simulated delay of 1000 milliseconds represents processing time. After processing the message, the method returns a greeting object, which contains the response. The @send_to annotation indicates that the result will be sent to clients subscribed to topic/greetings. This snippet demonstrates how a simple WebSocket message handling method could be set up in a Spring application. Spring GraphQL support. Spring Framework provides support for GraphQL, an open-source data query and manipulation language for APIs, as an alternative to RESTful services. This support allows developers to define schemas that describe the shape of the data provided by their server, issuing queries that fetch precisely what's needed. The provided code snippet defines a simple Spring GraphQL controller with a books query. @query mapping annotation is used to create a GraphQL query resolver, which maps the books GraphQL query to the books method within the controller. When a GraphQL query for books is made, it invokes this method, which returns all books using a book repository to interact with the data source. This illustration shows the simplicity of defining data fetching operations in Spring using GraphQL. Reactive Transaction Management. Reactive Transaction Management is a concept that applies to reactive programming in the Spring framework, allowing developers to orchestrate the execution of multiple operations on reactive types, e.g., Flux or Mono, across different backends while maintaining transactional boundaries. It ensures that all operations within the scope of a transaction will either complete successfully or roll back in case of errors. In the provided code snippet, we are using reactive transaction management with a Spring-managed bean transactional operator. It's used to declare a transactional boundary for reactive streams. The perform transactional operation method saves an entity using reactive entity repository. After saving the entity, another operation is performed on the repository. Both operations are wrapped in the scope of a transaction by calling as_rxtx transactional. The transactional operator checks for the execution result. If all operations complete successfully, the transaction is committed. Otherwise, it is rolled back. This allows for succinct transactional control in a reactive programming model.